Okay, we're going to start talking about Lewis structures today, and that's really just shapes and dot structures and things that you guys have done before. And so, like I said, you've learned this, but I want to kind of go back over it with you. And so, here's all the steps. You kind of start by counting the number of valence electrons. So, there is a term that we talked about, valence. And so, remember, the valence electron, we wrote that down in our periodic table. The valence electrons are going to be based upon the column that the chemical is in. So, for example, if you had a like oxygen, for example, oxygen is in column 6A, right? So that's the column that oxygen is in. So that means that oxygen would have 6 valence electrons. And so that's kind of something that we talked about earlier, that you kind of want to be able to look at those columns. So you should have that written down in your periodic table. If not, go back and it's in it's earlier on in the notes. Okay, place the least electronegative element in the center. Arrange the other atoms symmetrically around it. And so what happens is that we have these chemicals, and you put one of them in the middle. So like chemical A goes in the middle, and then every other chemical is going to get attached to the center, right? So normally something like that. And so we didn't see anything with 5 attachments last year, but we can have things that have 5 attachments, and they're called expanded octets. We'll see some of that stuff. But what you don't want is to kind of like draw things in lines like this. That doesn't work out. So it's always something in the middle, and then everything else is attaching to that item in the middle. So that's just something to kind of think about as we're moving forward here, is that there's always a middle, right? So if there's not a middle, which is possible, organic structures don't have middles, then a lot of our rules are not going to work. It's not that there aren't chemicals in big lines. It's just that most of the time we're not looking at those for these very specific shapes. So usually the chemical that's in the middle, you don't have to use your electronegativity chart. You can just literally look at the chemical. It's normally the one that's listed in the first spot. So as a general statement, it's always that first chemical listed. Now, if you have something with a hydrogen in it, hydrogen can never be in the middle. And so if you have something with hydrogen in that first position, then you're going to have to go to the next element. So hydrogen is too little to be in the middle. And so, might want to make a note of that here, that hydrogen cannot be in the middle. So let's go ahead and write that there. There we go. It can't be the central atom. There we go. Okay, so hydrogen cannot be the central atom. And so you're going to find that hydrogen is the exception to all kinds of rules. Okay, assign lone pairs around the atoms so that they get to the octet. So this is always a hard part for students. We actually build everything up to 8. We talked about that. We kind of watched that video. We bring everything up to 8, and then we work backwards. Again, hydrogen is the exception because it can never have more than 2 electrons. So basically, if you attach hydrogen to something, you have to leave it alone. Hydrogen can never have any dots. It can't have double bonds or triple bonds. Hydrogen is simply attached, and then you leave it as is. So it's easy. It's just you got to remember that it, again, is kind of a pain because of all the various exceptions, and they're all usually based upon hydrogen. So, all right. So let's take a look. Place any remaining electrons on the central atom. This is brand new. We did not do this last year, but here's the deal. If you need more electrons than you have, you put them on the central atom. And this is going to create structures that have more things on the central atom than they did last year. And so they actually are going to break the octet rule, where you can see things that have like 10 items instead of 8, or 12 items instead of 8. And then we manipulate the lone pairs in order to find double or triple bonds that could be in our structure. And then at the end, if it has a charge, you got to put brackets around it, kind of like this. And then you got to put the charge on the outside, So if it was a +2, it kind of looked like that. If it was a -1, it looked like that. If it was a -2, it looked like that. So that kind of thing, where your structure would kind of be in here. And then you got to tell the reader, hey, this also had a charge. And so that's why you've got to put that charge there, because you can't tell that it has a charge just from the dot structure. So, and that all means a whole heck of a lot of nothing to you unless I do an example. So let's just do a real easy example. So carbon dioxide is an easy example. And so let's draw a dot structure for carbon dioxide. So first thing is that you got to have an element in the middle. Well, first element is carbon, so we might as well put the carbon in the middle. That makes sense. Carbon loves to be in the middle, loves to bond with things, and so we'll put the carbon in the middle. Okay, so now at this point we need to attach the oxygens, and so we're going to attach both of the oxygens to carbon. So this is how I will do it, nice and symmetrical. But if you want to do something a little crazy, maybe you do that. That's pretty wacky, but still works. Or maybe you want to get even crazier. Maybe you get really wild and nutty, and you decide to do that. Yeah, that works too. So really, whatever floats your boat is fine with me, as long as everything is attached to the middle atom. I usually just keep them nice and symmetrical. I like to think of these elements as having a little box around them, like so. And in order for them to be stable, we have got to get to the octet, which means we need to get to 8 electrons. Okay, so what you need to do is you need to get these nice and stable. And so if we go back to our rules here, it says assign lone pairs around all atoms to provide an octet. Okay, and so we're going to go ahead and do that. And this is always a problem students can run into, is they want to try and solve it before they make sure it's stable. So if you think of this as a box, it has a top, which needs something there. So we put 2 dots, a left side, 2 dots, and the bottom, 2 dots. So every side of my box has an attachment. So see, this side is already got something going on, so I'm going to ignore it. This side has got something going on, so I'm going to ignore it. But the top, nothing, and the bottom has nothing, so I'm going to do that. And then again, this is attached, so we don't need to worry about it, but the top needs some help, the side needs some help, and the bottom needs some help. So that's what you do. You fill them up so everybody's nice and stable. Now remember, if there was an H attached here, we would not put any dots on the H because it's too little and it can't have any dots. All right, so let's go ahead and think about this. The directions on the other page don't talk about this specifically, but you need to see how many electrons are available. So what you do is you count the valence electrons available. Okay, so how many valence electrons are available? Okay, so oxygen is in column 6A, And so it is going to give us 6 valence electrons. So once again, if you don't know what I'm talking about here, got to get to my periodic table. I think it's actually at the end. Yep, there it is. So if you look here, I did this for you guys earlier. Oxygen is right here, 6 valence electrons, because it's in column 6A. And then carbon is right here, so it's going to get 4. So we're going to get 4 and 6. So we're going to remember those and slide back to where we were working. There we are. Okay, so there's 2 oxygens. So oxygen is going to give us 6 valence electrons times 2 for a total of 12. And then carbon is just going to give us 4. So we're going to add that up. And so my target, I talk a lot about target numbers, but my target number of electrons equals 16. I can have 16 electrons. Okay, so now we got to figure out what the heck is an electron. Now, there are electrons here in this bond, and there's electrons here in this bond. So basically, here's how it works. Everything counts as 2. So bonds count as 2 because they have 2 electrons in them. So like the oxygen has 1 here, and then the carbon has 1. So there's 2 electrons in there, right? So everything counts as 2. So what I do is I simply go and I count everything in my head, and I try to figure out how many electrons do I have. So I would do something like this. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. This structure currently has 20 electrons, which is too many. You got too many. If it said 16, awesome, we'd be done. But it doesn't, it says 20. So we have to go and figure out how to get this down to 16. So there's only one way to do that. You add a bond. So you add a bond wherever you want. So I'm going to add a bond here. When you add a bond, you have to take away a pair of electrons from each side of the bond. So this bond is connecting carbon, so I'm going to get rid of that pair, and this oxygen. But notice I didn't get rid of anything over here because that's not where the bond was. The new bond is here, so it attaches the carbon to the oxygen, so I took 1 pair from each side. So it works like this. Add a bond, remove a pair of electrons from each side so that you add 2, you take away 4. So if you recount, you're going to end up 2, 4, 6, 8, that one's gone, 10, 12, 14, 16, 18. We're now at 18. 18 is obviously not 16, which is our target, right? But it's closer. So what do? Well, we do it again. You now add another bond. So what you can do is you can create a triple right there if you like. That'll work. Or you could create a double right there. So you can have a double and double or a single and a triple. It doesn't matter. I'll go with the double bond. And so I'll actually change the colors so that we know that what we're doing here. So I'm going to add it there. And then I'm going to, actually I think go different color than that. I'm going to add the bond here. And then I remove a pair from each side. So carbon loses a pair and this oxygen loses a pair because they're what we attached. If we count again, here we go, 2, 4, 6, 8, 10, 12, 14, 16. Boom, we've got it. So there's your structure. What you did is you made sure everything was stable. And then you matched how many electrons you have right here to how many electrons you were supposed to have right there. And then you are super happy because you are going to get an A. All right, I'm going to pause it here because I'm going to run out of time.